Hey guys, in this video, we're going to be looking at energy basics. At the end of this video, we should be able to describe how potential energy changes as bonds are broken and formed, recall what system and surroundings are and discuss how they're related, calculate internal energy using heat and work, and understand what signs of them mean, know what a state function is, how it differs from a path function. You should be able to give examples of each, calculate the change in enthalpy using internal energy and pressure volume work, be able to state the first law of thermodynamics, look at constant pressure systems and how they relate to heat and enthalpy. And then again, knowing how the signs affect the process, whether it's endothermic or exothermic, sketch an energy profile diagram, and calculate enthalpies of reaction, and be able to determine how much of enthalpy you have, how much heat you have. So we're going to start out by just looking at a general definition of energy. So energy is the ability to transfer heat or do work. And then we define heat as energy used to cause the temperature of an object to increase. And then our work is the energy to move something. Okay. In this unit, we're going to be looking at what's called thermodynamics. And specifically, we're going to be looking at thermochemistry. So thermodynamics is the study of energy transformations. Thermochemistry is that energy of transformations, but in terms of a chemical reaction. So our thermodynamics of a chemical reaction. So we have potential energy. Potential energy is stored energy. And it's the one we're most concerned with when we're talking about chemistry. So we can have stored energy due to object's position or the chemical composition. Some examples include food and a boulder on top of a cliff. Okay, and then one of the most important types of potential energy that we look at is electrostatic potential energy. So here we have two charged particles that are going to be some distance apart. And it's going to be given by the following equation. E, electrostatic, EL, is equal to K, and this is a weird, funky K, times by Q1 times by Q2, all over D, where Q1 and Q2 are the charges on the particles, and then D is distance. So we see from this electrostatic potential energy that the greater the charge or the smaller the distance, the greater that electrostatic potential energy. And this is going to relate so much in chemistry. So please understand how this equation works. Higher charges, smaller distance, greater greater electrostatic potential energy. Usually that means it's harder to pull these things apart. And then our K, this funky little flat K, is a proportionality constant. So it's there in order to relate units. So it's 8.99 times 10 to the 9 joules times by meters over coulomb squared. Okay? So it's just relating the charge, the energy, and the distance. Okay? Let's look at kinetic energy, which is less important for chemistry, but still important. So this is the energy of motion. So when something moves, it has kinetic energy. And then we can convert potential energy into kinetic energy. So if we're at the top of a hill, that boulder example, and we push it over, it's going to convert that potential energy into kinetic energy. If we digest food, we start to warm up all the molecules in our body, converting potential energy into kinetic energy, so on and so forth. And then there's the whole idea of movement charging things, and so kinetic energy and potential energy are related to each other. They are going to be able to be converted from one to the other without any loss of that energy. Okay, so anything that's moving has kinetic energy. So all molecules that are above 0 Kelvin have energy, kinetic energy. All molecules or compounds have kinetic energy. I'm just going to abbreviate this as KE, kinetic energy, as long as they have a temperature greater than 0 Kelvin, which is everything, right? So 0 Kelvin is absolute zero. It's defined at the point at which there is no molecular motion. So absolute zero, no molecular motion. So anything above that 0 Kelvin, you're going to have molecular motion. Our energy equation for this, for kinetic energy, is 1/2 mass times by velocity squared. And you're going to want to have your mass, in this case, in kilograms. And then your velocity is going to be meters over seconds. So when you multiply it out, you get kilograms meter squared over second squared, which is equal to 1 joule, which is our energy, which is why we don't have a proportionality constant for this. We don't need to relate the units. They do it on their own. Okay. So a little bit more about those units. Our SI unit for energy is the joule, which is going to be abbreviated as a J. And I just wrote this, but I'm going to write again. 1 joule is 1 kilogram times by meter squared over second squared. You should have that committed to memory. And then another unit we use is going to be the calorie, which is abbreviated CAL, where 1 calorie is equal to 4.184 joules, and this is an exact number. Okay? And then you should be familiar with calories, or at least kilocalories, because that's what all food is given in is kilocalories. So 1,000 little c calories is equal to 1 big C calorie, which is also equal to 1 kilocalorie. So what we see on the back of a food label is a big C calorie, so 1,000 little c calories. Now, it's pretty hard to directly probe a reaction. So instead of directly probing a reaction, we oftentimes look at what the reaction itself is interacting with in order to determine what's going on with the reaction we're trying to study. So whatever we're trying to study, we call that our system. That's what we are studying. In chemistry, that's going to be chemical reactions, usually. I mean, we study other things. But for the most part, we're looking at reactions. And then we have our surroundings. That's everything else. Okay. So our system, what we're studying, the surroundings, we think about it as everything else, but usually we think about it, the things that are in close contact with the system, close enough for energy transfer to occur. So energy in terms of heat or work. So can it transfer that heat or that work? So we can take this right here and look at it. So this is a cylinder, and in that cylinder there's a piston, and then inside the cylinder is a reaction, H2 plus O2. H2 plus O2 are inside, and they are what we would call the system because they're what we're observing. The surroundings are going to be, again, everything else, but usually we just think about the cylinder itself and the piston, the things that are actually in contact with the system itself. So in this case, energy can enter or leave the system as heat or work, but matter is not able to leave. Okay, so this is close to an isolated system, but not exactly. So an isolated system is one where neither matter nor energy can escape the boundaries of the system. Thermos is an attempt at this, but isolated systems don't really exist because it's impossible to completely isolate the energy. But we can kind of think about isolated systems and apply the theory to a lot of things we're going to be looking at. Anyway, so this is a non-isolated system. This is a system that's able to interact, at least through the transfer of energy, with things outside of the system itself. And our system, H2 plus O2, going to H2O. Our surroundings, the cylinder and the piston, that transfer of energy from the system to the surroundings can be done through heat or work. So work, we can expand our gas or contract our gas, which is what's in here. And that expansion or contraction of the gas will affect where that piston is. So either work will be done on the piston by the expansion of gas, or work will be done by the piston if the gas is condensed. So, and then of course heat energy can be transferred from the reaction itself to the piston or the cylinder itself. Okay, let's look a little bit more at work. So work is given the symbol lowercase w. And it is the energy to move an object over some distance. So work is equal to force times by distance. So however much force you exert on an object, and the distance it goes will determine how much work has been done. So this is force. This is distance. And then, of course, we can look at our force equation, where force is equal to mass times by acceleration. So the faster you're pushing it, the more you're accelerating that object, the more massive it is, the greater the force itself. Heat, this is the transfer of energy causing a change in temperature. And whenever we have heat transfer, it's always going to heat from a hotter object to a cooler object. So heat transfers from a hotter object to a cooler one. Okay. Heat itself is given the symbol Q. And then, of course, there is no heat energy if we're at 0 Kelvin. Because heat is that molecular motion. So no molecular motion, no heat. If we're talking about temperature, temperature is going to be the measure of the amount of heat energy. We define temperature as the average of the molecular motion or the average of the kinetic energy. Okay, so heat and temperature, though related, are not the same thing. You can have something that has a very, very high temperature but not a lot of heat, or something that has a very, very low temperature but a lot of heat. It just depends on the amount. So heat is extrinsic, depends on amount. Temperature is intrinsic, amount independent. Okay, so when you're thinking about heat, that you have to think about how much of a substance you have when you're trying to determine how much heat it has. When we're thinking about kinetic and potential energy, they can convert between the two. So energy is conserved, so we can convert between kinetic and potential energy. So energy is conserved. It, however, can be converted from potential energy, I'm going to do PE, to kinetic energy, KE, and vice versa. Okay? And again, we're going to depend on the amount of kinetic energy to tell you how much potential energy you have, and vice versa because of that conservation of that energy. Which brings us to the idea of the first law of thermodynamics, where energy is neither created nor destroyed, it's conserved. And specifically, we're talking about during a chemical reaction, right? Nuclear reactions have their own set of rules because we're transmutating from one substance to another. So I would say that the energy of the universe is constant. Or again, if we're thinking about in terms of nuclear reactions, the energy and mass are constant. That being said, if a system or surrounding loses energy, it is absorbed by the surroundings or system, respectively. So there is that conservation. If a system loses energy, the surroundings will absorb it. If the surroundings lose energy, the system will absorb it. And then, of course, same idea as if it's absorbing energy. A lot of times we look at what's called internal energy, which is given a big E. So we've looked at internal energy many times, although we have not called it directly that. It also can be seen as a U, just as a note. But our change in internal energy is going to be given as delta E is equal to E final minus E initial. Okay? And anytime we have a delta E that is greater than 0, we are going to have a system where the final energy of the system is greater than the initial energy. So this is for a system. Let's do that. Therefore, energy has been absorbed by the system from the surroundings. Okay? This is called an endergonic process. And then if we have the opposite, if delta E is less than 0, the final energy of the system is less than the initial. Final is less than initial. And as a result, energy is released the system to the surroundings. And this is called exergonic. Okay? So when we think about our internal energy of a reaction, we're thinking about our E initial being our reactants, E final being the products. So E initial is the energy of the reactants. E final is the energy of the products. And when we think about the energy of a molecule in a chemical reaction, we're talking about the energy of the bonds. The energy of a reaction is stored in the bonds. We have what are considered higher energy bonds and lower energy bonds based on what type of bonds they are, what atoms are involved in the bond, if the bond, what the bond type itself is, how tightly those nuclei are held together. Okay, but in general, or always, it's always going to require energy to break bonds, and it's always going to release energy when bonds are formed. So energy is required to break bonds, as that is a unfavorable thing. So this would be endergonic. And energy is released during bond formation. So that is exergonic. Okay. Determining what the final change in energy is for a reaction, change in that internal energy depends on the energies of the reactant bonds, the energies of the product bonds, and how much energy is required to break bonds, how much energy is going to be released during bond formation. So energies are bond type dependent. So they could be single, double, or triple, and the atoms that are involved. So atoms in the bonds and bond type. Single, double, or triple. Okay. Okay, let's real quick look at our internal energy in terms of heat and work. So when we have energy, energy can only be exchanged through heat or work. So internal energy is exchanged through heat and work. We have an equation. Delta E is equal to Q plus W. So our internal energy is dependent on the amount of heat and the amount of work either done on the system or done by the system. So our change in our internal energy depends on how much heat or work is released or absorbed by the system. So it depends on amount of heat and work, as well as the signs of heat and work. Okay, so if heat is added or work is done on the system, both of these will result in an increase in internal energy. So heat applied to or transferred to or work done on a system both result in an increase in internal energy. So that's going to be a positive sign. All of those will be a positive sign. And then heat released or work done by the system decrease. This results in a decrease in internal energy. And a negative value. So when we're thinking about our heat work and internal energy, like I said, if we have a plus, that means work was done on the system or heat was gained by the system, and we have a net increase in our internal energy if both of them are positive. If we have negative for heat, negative for work, we've lost heat by the system, we've done work by the system, and combined they have a total decrease in our internal energy. We can kind of think about this in terms of a bank. Deposits of energy is positive, withdrawals of energy is negative. If one is positive and one is negative, it depends on the magnitude of the two. Okay, let's look at an exothermic process and an endothermic process. So when we're thinking about heat alone, so think about heating energy. So for excluding work, we can use the terms exothermic and endothermic. So basically, an exothermic process is one where heat is released, an endothermic process is one where heat is absorbed. So exothermic is going to feel hot because heat is releasing from our system to our surroundings. An endothermic process is going to feel cold because heat is being absorbed by the system from the surroundings, so the surroundings are getting colder. So exothermic, surroundings heat up. So this feels hot. In endothermic, the surroundings cool down because they've lost heat, and this feels cool. Okay. So some examples of some exothermic and endothermic reactions. Exothermic examples are going to include stuff like combustion reactions, neutralization reactions, and hand warmers. Some endothermic examples are going to include melting, evaporating, and then some dissolving processes. Which brings us to the idea of cold packs. Cold packs are generally, not all of them, but generally a dissolving process that is endothermic. Here is kind of just a visual of what that looks like, and energetically it would look like this. So our energy profile diagram, we're going to be looking at reaction progress versus energy. In an exothermic process, you're going to start out at a higher energy and go down to a lower energy, and it'll look like this. In an endothermic process, you start at a lower energy, go up to a higher energy, and it looks like this. And what we see here is something called activation energy, EA. Activation energy. And this is basically the energy that needs to be inputted in order for a reaction to occur. Okay, let's look at an example. So we've got a ball, it weighs 10 pounds, and it's raised 2 meters from the ground. Then it's dropped. We want to know how much work was required to raise the ball, and then when it was dropped, what was the speed of the ball just as it hit the floor. So we're looking at work here. So work is equal to force times by distance, and then force is equal to mass times by acceleration. So we could actually write work as mass times by acceleration times by distance by just replacing force with mass and acceleration. So we have a 10-pound weight, and that 10-pound weight, we're usually going to be dealing with, we want to get to joules because we're looking at energy. So to get to joules, we have to be in kilograms. So we need to convert this into kilograms, where a pound can be converted into kilograms by 1 kilogram equaling 2.205 pounds. And we get 4.535 kilograms. And then we can put this into our equation. Work is equal to mass, 4.535 kilograms, times by acceleration. This is going to be gravity, right? Because we're just dropping this. So it's 9.8 meters over second squared. So falling object our acceleration is equal to gravity. Okay? And then multiply it by our distance, 2.0 meters. And when we do all this, we get 89 kilograms times by meter squared over second squared, which is the same as joules. Now, let's assume that all the work can be converted into kinetic energy. Right? We've lifted up the ball and then we've dropped it. So the work that was required to lift the ball is then converted into kinetic energy as we drop the ball and it's moving. So we have our kinetic energy equation, 1/2 mass times velocity squared. So what we want to know is the speed, that's our velocity. So we're going to put our energy in, our kinetic energy, 89 joules, and that'll be equal to 1/2 our mass, 4.535 kilograms, times by our velocity squared. Now, we solve for that. Again, make sure we're in kilograms because we're trying to use joules. So joules are kilograms times a meter squared over second squared. When we divide our joules by our kilograms, we get velocity squared is equal to 39.2 meters squared over second squared. And then when we take the square root of that, we get 6.3 meters over second, our speed. Okay, acceleration is meters over second squared. Speed is meters over second, or velocity. Okay, one of the important things we're going to be looking at in this chapter is the idea of a state function. And it helps us to understand how different functions behave. So when we're talking about the internal energy of a system, the energy only depends on the present state of the system and the initial state of the system. It doesn't really depend on how it got to the initial state at all. So our delta E depends only on E final minus E initial. So it doesn't matter how we get from here to here, it just depends on the final initial. So it is path independent. Any function that is path independent, we call it a state function. So as long as that function doesn't depend on the path itself, it'll be a state function. Okay? For instance, if we have temperature, if we have water temperature at 25 degrees Celsius, it's going to have the same energy no matter how we heated that water, or if we cooled that water, right? It's still going to have the same kinetic energy, and it's still going to have the same internal energy. So it does not matter how we prepared that state. It just depends on the energy of that state at that moment. We can compare this to things that do depend on our path. So state function, independent of how the sample was prepared. But a path function depends on the path. Right. So a path function is going to be one where the initial state and the final state matters, but we have to take into account states along the way. So we have to look at each portion of the path. So we can see this if we look at this diagram over here. So in both cases, we have a battery. It's a charged battery initially, and then it's a discharged battery after it has been used up. So the energy doesn't matter, right? It goes from a charged state to a non-charged state or a discharged state. The final initial states are all that matter with the energy. However, if we think about how that energy is lost, it can be lost as heat or work, right? In the case of a heating coil, it's going to be lost by heat. In the case of a fan, it's going to be lost by heat and work. So our battery itself doesn't care how it's discharged, but the heat is going to be a path function and the work is going to be a path function because it depends on how much of each we do, right? How it's being used. So we would consider both heat and work a path function. Another way to think about this would be to think about pushing something, right? If you push something over a distance, it's going to be the same distance, right? Unless you go a different way. Then it's going to be a different distance. Or the speed at which you push it will determine how much work you've done. So it depends on force and distance to determine your work. Another way you could think about it is going up a mountain. You're going up a mountain, you start at the bottom, you go up to the top. You could go many different ways to get up to the top, and the amount of work you've done will be very different as to what path you take. But your final initial states are still going to be the same. So you can see if your final initial states are the same, but the amount of that property is different based on how you go about that property, then it's going to be considered a path function. So path function depends on more than just the initial and final states. So some examples here are going to include heat and work. Okay. Next thing I want to talk about is the idea of enthalpy, which is given an uppercase H as a symbol. So this is a thermodynamic quantity that is equivalent to the total heat content of a system and is related to heat flow. So this is not Q, right? This is different from Q. So when we think about a constant pressure system, processes at constant pressure, the heat absorbed or released equals the change in enthalpy. So for a constant pressure system, the heat absorbed or released equals the change in enthalpy. Okay. We can solve for our enthalpy by taking our internal energy plus pressure volume work. Okay. Pressure volume work, we're going to be thinking about what is going on with a gas. So pressure volume work is due to the expansion or contraction of a gas. Okay. So in the case of pressure volume work, our pressure is remaining constant. And the only thing we're changing is volume. So our volume is V final minus V initial. So that change in volume is going to be a state function. So our work itself is equal to negative P delta V. Okay. The units here, you see, or the sign here, you see it's a negative. So work is equal to the negative P delta V. We have to think about this in terms of how our volume is expanding or contracting. So if we have a system and we've expanded that gas, our work is done by the system. So expansion of a gas, work is done by the system. Okay, so we've got an expanding gas, work is done by the system. And in that case, your V final is going to be greater than your V initial, so your delta V is going to be positive. But because it's work done by the system, the work itself has to be negative. So if this is positive and this has to be negative, that negative has to be in that equation in order to take that volume expansion and taking it to a negative. And of course, pressure itself will always be positive or zero, so it's not going to be affecting our sign here. If we have a compression of a gas, here work is done on the system. I forgot, this should be here, W should be positive, right? So work is done on the system itself, but our V final is going to be smaller than our V initial, so this delta V will be negative. In order to have a work that's positive, we have to have a negative sign there. So that's kind of just decoding why we have a negative sign in that equation. Okay, let's try an example. So we've got a reaction. A plus B goes to C, and B are gases, C is a solid, and it's done in a piston. Okay, so as the two gases react, they're going to form a solid, and during this, the system is going to lose 1150 joules of energy to the surroundings. As heat to the surroundings. Okay, so in this case, we've got a compressed gas, or a gas that is being compressed as the reaction occurs, so work is also done on the system. So as the piston moves down, 480 joules of energy of work is done on the system. So as the gas goes to a solid, 480 joules of energy, of work energy, is done on the system. We want to know what our internal energy is. Okay, so here we have delta E is equal to Q plus W. So our heat plus our work. We now have to think about our signs here. So if heat is lost by the system, so heat is lost by the system, that is a negative sign. So our Q is equal to negative 1150 joules. And then work is done on the system, so that's going to be positive. So work is positive 480 joules. Now we just put it into our equation. Delta E is equal to negative 1150 joules plus 480 joules. This gives us a delta E equal to negative 670 joules, which results in a exergonic process. And exothermic because of that negative heat. Okay. Let's look at some enthalpy equations. So enthalpy, one of our most important terms in this chapter. Enthalpy is going to be, as I've already shown, as our E plus our pressure volume work. And then if we want to look at a change in enthalpy, which is what we almost always look at, we're going to take that delta, apply it to this equation, and what we get is delta H equals delta E plus P delta V. Pressure, again, is constant. Pressure is constant. So our P will not have a delta in there because that delta indicates that you have a change. All right? Now, we can hopefully remember that work can be in terms of pressure and volume. So work is equal to negative P delta V. Just looked at that. And then we also want to recall our internal energy equation, where delta E is equal to Q plus W, our heat plus our work. So when we put all of this into our enthalpy equation, we get delta H is equal to Q at a constant pressure plus work minus work. So we'd say that our delta H is equal to our heat if we have a process that has a constant pressure. So for a constant pressure system, we have our heat flow, Q, equal to our enthalpy. If we do not have a constant pressure system, we do not have this being true. Okay. Let's look a little bit more at enthalpy, exothermic, and endothermic processes. Real quick, as a note, for most reactions, our delta E and our delta H are going to be basically the same as long as there's not a lot of pressure volume work. And our work component itself is very small. Okay. Another note, if we have a delta H that is positive, this means enthalpy or heat is absorbed by the system. And we call this a endothermic process. If our delta H is negative, then heat is released by the system. And this is going to be an exothermic process. One of the most important aspects of our enthalpy is enthalpy of reactions. We're going to be looking at lots of enthalpies of reactions. So delta H of a reaction is an enthalpy of a reaction. It's given by H final minus H initial. And since we're talking about a reaction, this is the same as our energy of our products minus the energy of our reactants, or enthalpies. Okay? So this can give us how much heat is lost or gained during reaction, and it'll tell us if the reaction is generating heat or if it is absorbing heat. Let's go into some enthalpy facts. So enthalpy is a state function. Unlike our heat, heat is not a state function. Heat is a path function, but enthalpy itself is a state function along with pressure, volume, and internal energy. Okay. It's an extensive property. It depends on amount. Okay. And we talked about a delta H. It's usually given in kilojoules per mole. So we can see that extensive property about it. Our delta H of our reaction is going to be the same magnitude whether we're talking about the reverse or forward process. It's just going to have the opposite sign. So for instance, if we have a delta H for your forward reaction, it'd be equal to the negative delta H of the reverse reaction. Okay? And our delta H depends on the states of the products and reactants, so physical states are very important. So pay attention to those. They're going to have different enthalpies based on whether you're a gaseous state, liquid state, or solid state. Okay, let's try out an example. So we've got the combustion of methane. In the combustion of methane, negative 890 kilojoules of energy per mole is released. If you have 25.8 grams of methane, you want to know how much energy is released during the combustion. So for every 1 mole of methane, it releases, so it's going to be negative 890 kilojoules of energy. So we also have an amount of methane. So we would write our delta H of our reaction of our combustion equal to negative 890 kilojoules per 1 mole of methane. We don't even need to write our balanced equation here, which is really nice. All we need to do is write out or convert from grams into moles into energy. So we've got 25.8 grams of methane using our molar mass of methane, where 1 mole of methane is equal to 16.043 grams. We can convert into moles of methane, 1.6125 moles of methane. And then from there, we can convert into energy using this right here, where 1 mole of methane releases negative 890 kilojoules of energy. And this gives us negative 1435 kilojoules of energy for 25.8 grams. And then we want to go ahead and make sure we put it in the correct number of sig figs. In this case, we want 2 sig figs because we only have 2 here. So it's going to be equal to negative 1400 kilojoules of energy, or 1.4 times 10 to the 3 kilojoules to remove any ambiguity. Okay, that is our energy basics. I hope you guys understand a little bit more about internal energy and enthalpy, work and heat and state functions, all sorts of stuff. This is very long, very, very long video. But I will talk to you guys later in the next one.